We are live again, and the second talk today, which is about saving assemblies to disk by Victor from Paris. Hello, Victor.
Hello there.
We
Thank
are
you for having
super.
me.
Yeah, exactly. Thank you for being with us. So this is a thing we love, like internals, and IL in the name is even the best thing we can have, like low-level stuff in the title. So we are happy. So everyone, please watch the talk. If you will have any questions, do not hesitate to ask on chat or on Discord. I will provide a link to a Discord in a second. And without further ado, I will not take your time. So please, the scene is yours. I'm hiding myself and listening. Thank you.
Well, I'm really happy to be able to give this talk because I've been following Dotnetos for a while now, and I've always been very impressed with the quality and the deep dives into real technical stuff. So I'm honored to be able to contribute my own little piece of knowledge to today. So I'll be talking about ILPack, which is an open source package by Locat, and its purpose is to let you take an assembly from memory and save it as a file on the disk so that you can reload it from the disk later on and get the same assembly back. So before I dive into the details, I just want to do a quick recap about what an assembly is and why it makes sense to want to save it to disk. So in the .NET world, you start with source code in one of the .NET languages. You have source files, you have a project file, which acts as sort of a container, and you compile this to an assembly. So the assembly is going to be usually a DLL file. It contains types, the methods, the fields, and the actual executable code is encoded as CIL, the Common Intermediate Language. And if you want to execute .NET software, then the first step is to load the assemblies into memory. Now, the CIL cannot be directly executed by the processor, so there is one final translation step that needs to be done just in time to produce the actual executable machine code. And there's an interesting feature in .NET, which is that you can produce at runtime new assemblies with new types, new methods, new CIL, which will again be just in time translated in order to be executed. So this is really a very high-level overview, and almost everything I've said so far has some pretty big exceptions, but this is what you need to know in order to understand what's going to come. So what ILPack does is it does the opposite of that load step there in the middle. And it's not obvious to achieve because the memory layout of the assembly in the file is not the same as in memory. The loading step does a few things, such as resolving references between assemblies, and all of those steps need to be undone by ILPack in order to produce the file. So my goal today is to answer three big questions. First, why do we want to create assemblies at runtime? Why do we want to save them? And how is it done? So to begin with, a little background about myself. I started working professionally with C++ back in '99. I was working on video games on embedded platforms. Maybe some of you remember the Pocket PC and the small tablets, PDAs. They're all dead now, so there's almost no way to play those games anymore. And in about 5 years later, I moved on to C#. And those were the very early days of .NET. It was still closed source. It was Windows only. So framework 1.1, we didn't even have generics yet. And at that time, I joined an open source project called Ngrid. So that's how you can tell it was a .NET project from the good old days. We had to start our names with N so that people would understand that it was about .NET. So Ngrid is distributed execution framework. So I'm not going to show you actual Ngrid code because it was from the days of C#1 and it has not aged well. So just to give you the general idea, this is some pseudocode. So you would run your application on a cluster of machines. And on any of the machines, you could create an instance of a .NET class. So here I'm creating a cat called Mittens. And you could send an instance to another machine, which would serialize the class, send it over the network, deserialize it on the other end, and it would destroy the local object and replace it with a proxy that you could use to refer to the remote object. And you could then use the proxy to invoke methods on that object, and those methods would be executed on the remote machine. And if you had return values or if you had exceptions, those would come back to the local machine. So this is really a basic building block for creating more complex distributed computation scenarios. And the price that a .NET developer had to pay in order to use this was fairly low. Basically, for every class that you wanted to control remotely through a proxy, you had to create an interface which would be implemented by the proxy and which exposed all the methods you wanted to call remotely. And coming from C++ as I was, this was absolutely magic. Because in C++, you would have to do everything yourself. The framework did not help you. .NET did not help you. So if you wanted to send a cat over the network, you had to serialize it. And if you want to get a sequence of bytes from a cat, you want to irritate the cat. And in C++, you would have to write the code to irritate the cat. And same for the proxy. You needed a proxy, so you wrote a proxy class in C++, and you had to implement methods. So you presumably would get access to some kind of network connection and send messages over it, wait for responses. So that was a lot of work. And the point of ngRid was that none of this was needed. So the way it worked is, well, first, system.reflection. It's been there for quite a long time now, and it allows you to use C# as a dynamic programming language. Think like JavaScript or Python. So you could write a serialization function which traversed all the fields of an object of any type and recursively serialize the fields of that object. And there you go. You have a serialization function. It's generic. However, there was a little bit of problems with performance there. So methods like getType or getFields, those are traversing a static web of objects. It's all static typing. It's all very fast. But as soon as you start using things like getValue or setValue or invoke method, well, those were slower. Think 1, maybe 2 orders of magnitude slower than handwritten C# code with static types. So in order to get a bit of performance, people would use system.reflection.emit. And the idea behind emit was you would create a dynamic assembly. And it would contain the same kind of types and the same kind of IL as something generated by the C# compiler. So you would expect to get same level of performance, especially since the JIT would be able to do the same lowering of your code as standard C# assemblies. However, it was a painstaking process. Think for a 10-line C# class, to define the equivalent thing using the system reflection emit APIs would take between 60 and 70 lines of just calling methods to define assemblies, define types. And the code that you had to generate, it was actual CIL. So you emitted the CIL one operation at a time. But still, it worked. It was pretty fast. So that was the niche for system.reflection.emit. It's when you need dynamic behavior and you need it to run as fast as normal C# code. And there were plenty of libraries that relied on runtime code generation. JSON.NET used this to generate serializers and deserializers that were extremely quick. WCF, the Windows Communication Foundation, which was basically what ngRid hoped to be, but a lot better, also used this to implement proxies. You had dependency injection frameworks. You had mocking frameworks for unit testing. All of these needed dynamic behavior and used some form of runtime code generation. Then things changed. In the last 18 years, there are a few major changes that impacted the way we do runtime code generation. And one of them was in 2007, it was LinkU. So that was the flagship feature of C# 3. I believe it was .NET Framework 3.5 at the time. And so LinkU, well, it brought a new syntax based on SQL to create queries over datasets. But the real interesting thing was that LinkU could look into the query, and it could cut the query into two pieces. One of the pieces would be compiled as SQL and sent over to a database. Hopefully, this would result in a dataset that would be smaller than just fetching the entire table. Fewer columns, and if you had filters, it would also retrieve fewer lines. And the rest of the query would be executed on the .NET side because it involved things like creating instances of .NET classes, which obviously cannot be done on the database. And this separation actually happens at runtime because if your dataset wasn't a database, but it was actually a list in memory, then all of it would need to be done on the .NET side, and you didn't want to have to rebuild your application to change dataset sources. So this really sounds like there is some runtime code generation in there, and it is. Microsoft even made it available publicly instead of just keeping it hidden inside LinkU. So how does it work? Well, first, the syntax is nice, but there's an equivalent syntax based on extension methods, which I believe is the more popular one these days. So the first would be just lowered to the second after the type inference was done. And it was the second one that actually was used by LinkU. So if I wanted to implement this using normal C#, I would write an extension method. So it's an extension of IEnumerable, or maybe IQueryable. And it gets an argument, which is a predicate. So that's a function which takes an element of that specific type and returns a Boolean. And now if I want to look at what the predicate is doing, well, it is a black box. That maybe I could get access to the bytes of the actual IL inside the function, but even then, it might not be something that involves IL at all. Maybe it's a p-invoke predicate of some kind. And what was added by LinkU was an expression type. And this actually relies on help from the compiler. So where the compiler sees a call to a method which expects an expression argument, and the argument that is passed is a lambda expression, then instead of generating the normal code for the lambda expression, the compiler would generate a tree of expressions. And it is a lot more readable than CIL. It's a tree of expressions with the typical things like binary operators, constants, member access, variables. So this was really a leap forward. Before that, you could do introspection in C# using system.reflection, but you could only look at types, methods, fields, not at the code itself. And LinkU expressions really lets you look at the code inside the lambda expression. And not only that, but you can also extend this. You can create your own expressions, either from basic building blocks or by modifying an expression that you received from the compiler. And it actually supports more language features than just what is available in C#. For instance, you get access to loops, throw statements, try-catch. So it really was intended as a target for code generation and not just a way to do introspection in code. And of course, there is a compile method which turns an expression into an actually callable lambda. So this function would then execute with the same performance characteristics as if it had been generated from C# code. This is very nice, but there are a few limitations. The first being you can only define functions, so you cannot define types, and so you cannot implement interfaces. So for things like the proxies from the previous example, that would not work. The second problem is that, well, the CIL is by definition the output format of the C# compiler. So whenever C# gets new features, the CIL also gets the corresponding support for those features. But LinkU expressions are frozen in time at about the level of C# 4, which means there's a lot of new features in C# which are just not supported. The main example that I find important would be span of t. So most of the really important things, the things that make span of t important, are not supported at all in expression trees. So if you are given a choice between link expressions and system reflection limits, if you can use link, do use it, because for debugging and for code clarity and for succinctness, it's a lot better. But if you really need the hard low-level features, you'll have to use reflection.emit. And then there was another big change, source generators. So I'm not going to say much about this because yesterday Stefan gave a really excellent talk about this at the Dotnetos Conference. I will just say a few short words about why it is relevant, because it is certainly not runtime code generation. So this falls into the general concept of ahead-of-time compilation. So having the C# compiler produce executable machine code instead of producing IL. And so it does not need this .NET runtime in order to execute. Now, this is good news for a lot of reasons. You don't have to distribute the .NET runtime anymore. It's just a normal exe. But it also has the downside that you can no longer generate code at runtime because there is no runtime to JIT that code and run it. So all the libraries that previously relied on runtime code generation, such as JSON serialization, will now slowly migrate to source generators, which do about the same thing, but they run at compile time. And instead of using system.reflection to inspect the types and the methods, you use compiler APIs to read those, and instead of using system.reflection.emit to produce new methods, you use the compiler APIs to emit new code. I expect that migration would work over the next few years, but there will remain, I believe, things which still rely on runtime code generation, which I personally hope that AOT will not become the main or the only mode of compiling .NET. So let's talk about Locat. I joined Locat in 2020. 12, oh my God, my English. So 2012, okay. And it's kind of a weird company. So it's the kind of company where if you have a problem and you would think, well, creating our own programming language is the solution to that problem. And everyone would think, well, okay, so we created Envision. And Envision is a domain-specific language for supply chain optimization. So to give you a little bit of overview of what we do and why we needed programming language, well, supply chain is a very diverse field with many different kinds of problems which are related conceptually, but actually have very major differences that cannot just be abstracted away. So one example, we have a customer with a central warehouse, and every morning trucks leave from that warehouse to deliver products to all the stores around the country. And you want to make sure that every store has products in stock in case a customer comes in and needs them. But you have some stores which actually sell more than others and don't have room for too much inventory. So for those, you might want to keep some parts, some products in the warehouse rather than send them to a low throughput store, just waiting for the high throughput store to have some room and send it to them. So every day you're looking at something like 10 or 20,000 individual decisions for your supply chain. And Locat writes software that makes those decisions for the customer. Another example is a client from the fashion industry. So they have seasons and they have discounts. So they put on sale those products. And their goal is to drive the inventory levels towards zero exactly at the time that the season ends. You don't want to reach zero too late, because then you have dead inventory after the season has ended. But you also don't want to reach it too early, because if you reach zero inventory too early, it means you could have kept your prices a little bit higher until then. So every day there is the decision for every product in every store of what the discount level for that product should be. And it's entirely dependent on the current inventory and on the expected speed at which the products will be sold. And again, Locat wrote software which makes those pricing decisions for customers. So this means there is a lot of client-specific code at Locat in our code base. And we wanted to avoid the situation where we would have many supply chain experts go out, talk to customers, gather requirements, come up with solutions, and then come back to a software engineer and let the software engineer do the actual implementation. This approach has some very bad downsides. One of them being that, well, the person who knows what needs to be done doesn't know how it is done or if it is even possible in the first place. And the person who does the things, they don't have a clear understanding of why those things are being done. So we created a programming language for this purpose. Envision was created with the fundamental requirement that it should be faster for the supply chain experts to do the thing themselves using Envision than to let a software engineer do the implementation. And it is quite a challenge, but we managed it. And so Envision is relevant for ILPack because of the way it is executed. So we have execution clusters, and those clusters are running constantly a .NET process, which waits for scripts to be submitted for execution. And it can run several scripts in parallel. So when you submit an Envision script along with the input data that needs to be processed by it, the execution cluster would, well, first compile the script into a series of executable steps. Some of these steps are going to be handwritten bits of C#. For very generic things like parse a CSV file or sort this very long vector of records, or maybe some very specific optimizations for supply chain that are generic enough to be reused. But then there's all the glue around that. Things like filtering data, shuffling it around, doing some aggregations and statistics, and general applying business rules that cannot be handwritten because they are specific to every customer. And we want this to run fast because, well, again, we're talking of terabytes of data and we want a result quickly. So we decided to do runtime code generation. So this CIL is intended to be very fast. And we rely on the .NET JIT to produce very fast code for those operations. And this is something that cannot be done at compilation time because, well, the execution cluster is running and running several scripts in parallel. So we do not know in advance what scripts will be submitted, and we cannot stop the cluster in order to rebuild it with compile time code generation. So that's why we create assemblies at runtime. And I'm sure there are many other reasons, but those are the ones that I found important. Now, why do we want to save them? We want them in memory in order to execute them, but why save them? So what happens when you write a compiler? Obviously, you make mistakes. There are two main mistakes that you can make in a compiler. One of them is that you generate invalid code, just doesn't make sense. Or you write code which is valid, can be executed, but has bugs. For instance, it gives the wrong results, or it throws an exception because you have an out-of-bounds access or something like that. And how do you investigate those issues? So this is what it looks like to generate invalid IL. It is a very unhelpful exception. You get absolutely no details beyond this is invalid. And so it makes sense because invalid CRL should be something that is sufficiently rare that we don't want to spend precious resources in the .NET runtime to actually provide diagnosis of why it is broken. So we would use normally out-of-band tools that look at the DLL file and tell us why that DLL file is invalid. But we don't have a DLL file. Now, we do have access to the bytes. Like we can get the IL as a byte array, but this is not directly usable, neither by humans nor by software. But good news, .NET Framework has a save method on the assembly builder. So if you generated dynamic code, then you have an assembly builder in hand. So you can save it to a DLL file. And there you go. You have a file on the disk, which you can pass to the other tools. So what kind of tools? The first one I need to mention is ILverify. I wanted to mention it mostly to say that I am really not convinced by it. It has the advantage of being completely command line and portable, but it is very brittle. If you do not pass the correct arguments in the exact correct way, it can blow up. And some of the ways in which it can blow up is just unhandled exception stack traces. And you have no idea what you need to change in order to fix that null reference exception. So it takes some time to get used to it. And even though you can manage to get it to output the actual correct error, you still need a disassembler to look at the IL at the location that is identified by ILverify as being the problem. So for invalid IL problems, I tend to use ILSpy. So ILSpy is an open source decompiler for .NET. Its main purpose is to produce C# that corresponds to the methods inside an assembly. And when a method cannot be correctly decompiled because it is invalid, it will still do its best. I wouldn't trust its output, but it still does its best. And very importantly, it gives error messages, which can help identify what the problem is. Multiple errors can happen because obviously when the code is broken, it can cascade and provide several errors in a chain. Here, the important one is the incompatible stack heights. And it has a location. And I can switch to the IL view and go to that location and start investigating, well, why are the stack heights different? Probably because I generated something which consumes more stack than the other or less stack than the other batch. The ability to generate C#, to decompile into C# is also very useful when you're trying to debug valid code which just has bugs. Most humans are a lot more adept at understanding C# than IL. Well, think about most humans. Well, most humans probably can't do either, but people who work in the .NET environment are better at reading C# than IL. There is another tool which I actually prefer when it's a matter of reading C# code, which is .peek from JetBrains. So this one is not open source, but it is still free. You don't need a license in order to use it. It is useless if you have invalid IL. It just gives up and says, I couldn't decompile. But in the cases where you manage to compile, it has a very interesting side-by-side view, where you can click on a statement on the C# side, and it highlights on the IL side the statements that correspond, and vice versa. And it's really important because you're reading on the left side because that's what you can understand, but the bug and the thing that you will need to fix is on the right side in the IL because that's what your compiler produces. But why do we need ILPack? I mean, I just said we had a way to produce the DLL file on the disk. Well, I have some bad news. In 2016, .NET Core came out. Actually, it was out for maybe 2 years for the very eager people who wanted to see it before that. And obviously, the first version of .NET Core did not support all of the APIs in the .NET framework. And among those was assembly builder.save. And it has been 7 years now, and every so often, there is a message on this specific GitHub issue saying, we're looking into it again. We're trying to prototype something. I think the last one was from last July, maybe. I've become a bit jaded, so maybe it will happen at some point in the future. I don't know. So In the beginning, this was not a huge hindrance for us because it was a debugging tool, and so we could just run production on .NET Core. And if we had a bug, we reproduce the bug on .NET Framework, and we use .NET Framework to save the assembly and do the debugging. IL was compatible between the two, and we generated the same in both cases. So that was fine. But then, well, .NET Core started evolving, getting more features. C# started getting features which are no longer backwards compatible with .NET Framework, and we were really limited, like not being able to use more than SIMD for spans, or using the memory-based methods for streams and so on. So we decided that we had to migrate. And so we created ILPack. So the point of ILPack is really to provide an API which lets you save an assembly. So it's fairly similar to the one in assembly builder.save. The main difference being that you don't need an assembly builder. You can just get any assembly in order to produce the DLL file. And the behavior is about the same, and we intend to support all of the features available, so any assembly should be able to be saved with. Now for the interesting details of how it is done. So I'm not going to give you a complete overview of everything in there. There's a lot of stuff, but just give you enough information so that if you want to look at the code, you can find your way around it. So the first thing that you need to know is that it is really a bridge between two parts of .NET that are really complete in what they do. On one side, you have system.reflection.assembly, the class, and all its related types like method info, property info, and so on. And the important property here is that inside the assembly, you have all the information that is needed to serialize it, only through this API. We had to invoke almost no black magic in order to access private fields that we are not supposed to access. And on the other hand, on the other side of the bridge, we have system reflection metadata ECMA 335, and specifically the metadata builder class. This one is able to serialize an assembly as defined by the builder to disk. It's just you have to call the builder method yourself to build the assembly before it can be saved. It cannot just take an assembly and save it. So ILPack is mostly about traversing the assembly contents using reflection and calling the right methods on the metadata builder before finally dumping it to a file and everything is done. Most of it will be just mapping enums. So it's not the most of it by importance, but it's most of it by volume, because there are many enums and many attributes all over the place that have almost no depth in terms of semantics. You just have to copy the flags. It's just the same. On the other hand, there's also the question, the more deep questions about, well, it's all about tables, and you have to generate them, and you have to know what all of the tables are. So you have tables for classes that you define. You have methods are in a table, constants are in a table, events, as in the C# events, are in a table, properties are in a table, and so on. Some very weird things are going to be tables as well, such as a class implementing an interface. That's not something that appears in the class table. That's a separate table which has a reference to a class and a reference to an interface and says, well, this class implements this interface. And those references are integers, because all of those tables are actually indexed by the position in the table of the row that you are looking at. And this does create a few problems, because definitions can be mutually recursive. And so to generate a reference, you need to know the position at which that element will be placed. So again, this is not difficult from an algorithmic point of view, but you still have to do a first pass, assign numeric identifiers to everything, And then on the second pass, when you generate everything, you have to make sure that everything is output at the correct place in the corresponding table. So a few specific things are going to be encoded as fairly complex binary values instead of being C# types, C# objects. One example of that is types. So if you want to reference a type that is just a class, that's very easy. You can just use the position of that class's row in the assembly, and you just get a reference. But if you're defining a return type for a method, or an argument for a method, or the type of a property or field, you can actually build types that are a lot more complex. You can have arrays of existing types. You can have generic types with parameters. Actually, I provided a tuple as an example, but a tuple is just a value type, generic class with its arguments. And the names of the fields are actually not even in the assembly. Well, they kind of are. They are encoded as attributes, but they are only used by the C# compiler. They are not actually visible to .NET. And you also have where if you're defining a generic method or a generic type, then the generic type parameter can also be used in types. And this is not even a real type. It's just a parameter. So basically, in terms of format, they gave up and said, well, this is just going to be a binary blob, and there's a specific serialization way to encode a type like this. Another complex situation is method bodies. So I would expect method bodies to be blobs because, well, CIL has variable width, so you cannot just have an array of fixed width instructions. So here are some examples. So every instruction has 0 or 1 operands. Add has no operands, it just pops 2 elements, adds them, pushes the sum. Load constants, integer 4 bytes, has an operand which is a 4-byte integer constant. So that's very easy to encode. Branch has a target location, which again is going to be, if I'm not mistaken, an int32. Call has an operand which is a method. How is that encoded? Maybe it's just the number of the method inside the method table. Hello, well, load string, loads a constant string, and is instance, the operand is a class, or actually a type. So for the last three, the encoding is a bit complex. They didn't want to actually encode those directly into the method bodies, so there is a level of indirection. So for strings, there's a table in the assembly of user strings. And so you get an integer reference, and you just write it after the load string instruction, and all the user strings are there, which is actually separate from the table of strings, which is used for things like function names, class names, and so on. Then for the types, well, maybe the type is something that you can reference by its number because it's a simple type, like maybe it's one of the types in this assembly. But if it is a complex type and it needs a blob in order to be saved, well, you have a table of type specs. And type spec is just a type blob serialization that you can use to reference complex types. And the same goes actually for methods. Have a method spec because not all methods have an identifier because they're in a table. Sometimes there are methods of a generic type, so you need to provide the type arguments for that generic type. That's going to be a type blob. And sometimes they are themselves generic, and again, you need to specify the type arguments there. Again, that's going to be a blob. So that's about all for the interesting things. So Locat ILPack is open for contributions, so we welcome use cases, especially cases where we do not manage to serialize something correctly. Issues are welcome. Pull requests if you feel like it, although if it's a big pull request, I recommend you ask first about it. So the link is over here. Right now, we don't plan on retiring this. We will probably plan on doing so if we have confirmation that .NET does support this natively. But until then, well, this has to work, so we keep on using it. If you want to reach out to me specifically, and not about ILPack, but just to have a chat about .NET or compilers or even Locat, that's my email. And I guess it's time for questions.
Hello. Okay, so now is the time for questions. Thank you for an awesome talk, like a meaty one. So we will talk and give you like 2 minutes maybe for questions if you have any. I have one question because it is super awesome thing, like a lot of low-level interpretation of all this metadata, saving it, mapping it. It sounds, and it is in the heart of your system, right? It is really earning money. So the question is now, how do you test it? Is it covered like a crazy by tests in various edge cases, strange code? Because, you know, every time when you can save something that is user generated, it is just exposing every possible edge case. So do you have many tests?
So there are the public tests in the open source repository itself, where basically we have assemblies, we load them, we save them, and we check that everything is fine.
Okay.
Then we have the internal Locat tests, because we are using this software in production. And basically, we generate about 1 gigabyte of CIL per day. And whenever we have a problem, we dump the dynamic assembly with 1 gigabyte of data inside it, and we reload it and investigate.
Awesome. Sounds like a nice job. Challenge, at least. Not a problem, but challenge. So do you find any interesting edge cases, like something which is not specified, maybe some problems that you need to refer even to the .NET team because there was some ambiguous, you know, parts of it?
There are a few ambiguous things. I don't have the exact details in mind, but surrounding generics, for instance, where you have various variants on a method, like the generic one on the generic type, and the one being called on the generic type during its instantiation, which has the type parameters, but it's not exactly the same, and so on. I don't have the exact details, but I do remember having to actually test the things and see that, well, those two things are usually equal. There's nothing in the spec that says that they have to be equal, but I guess we can use it. There are many like / to do left in there. One of the surprising things is that, well, it's obvious and well documented, but the order in which generic type parameters are defined. So there's a whole separate table for them. It's not a property of the type definition. You have a type definition, and then elsewhere you have a table which says, oh, by the way, this has a generic parameter. And those have to appear in the exact same order. And I think that's the only case where the order inside the tables is relevant. Everywhere else, just references, and in this specific table, they have to be sorted by the order of the other table, which I suppose is a performance optimization.
Nice findings. And by the way, because this is on the IL and metadata level, right? So it is something that probably should not change from .NET version to version. Is it true? Or do you expect that at some time something will explode? There should be backward compatibility at least, sure, right?
A lot of C# features are actually implemented as attributes. So, for instance, the value tuples with the names in them, it was implemented as a normal generic type, and the C# compiler gives a specific meaning. But previous compilers, and for instance, F# compiler, just doesn't look at the attributes and sees something which is backwards compatible. Also interesting was the way in which they added the generics back in the day because they didn't have them from day one. And they kept compatibility by saying, well, the generics are going to be a completely separate table, so that if an old version of the compiler doesn't, or the runtime doesn't know how to interpret those parts, they can just ignore them, and they still see the actual types and the contents. So for tooling, this is really important because it's not just the compiler and the runtime, it's all the tools around it that can look at the assemblies. And maybe your favorite tool is from like 5 versions ago, and you still want it to kind of work, maybe, please.
Right. Okay, the very last and the very first at the same time question is on the chat. Very general one. Do you have any advice for junior developers? So probably we can put it in the context probably of how the hell you have learned all these things?
Yeah. I say nothing replaces experience. And the one mistake that you can make is having the same 1 year of experience 10 times instead of having 10 years of actual experience. You need to get out of your comfort zone. You need to try and find out what is happening and why and how, and really look behind the scenes behind all the frameworks. Like I've talked about frameworks doing magic things. All the magic can be explained. And it's really interesting to see if you can, on your own, find ways to re-implement that magic. Maybe not to the same level, but it really helps not only with understanding the platform, but understanding development in general, programming in general, and any new experience is good.
So you need to get your hands dirty by trying to write or modify or contribute to something that you are using, right?
Yeah, you should try to fill in the holes in your understanding of the tools that you are using.
Exactly. For example, by contributing to the ILPack.
For example.
For example, exactly. Okay, we will be slowly ending because the time is ticking. So very much thank you for this talk. I hope we will see somewhere on the conference, and thank you. See you somewhere. And we will see, and you can also obviously attend the next session that will be in 15 minutes, which will be about the scalability of architecture and systems. So see you then. Thank you very much.